Ready? Thank you. All right, this is just a introductory material here. The key thing here is UAVs allows to have flexible deployment. Flexibility comes because of the mobility. At the same time, mobility also causes a problem. Mobility is good for moving around, and then we can place the vehicle where we want. At the same time, the same mobility causes issues in terms of network connectivity, network disconnections, and all that. And then we also have seen UAVs have two purposes. In one case, UAV itself is like a phone, and you can imagine that as if each UAV, each drone is like a phone, and you are trying to provide communication support for the drones from the ground. That is one scenario, which is whether we could use cell towers or cellular service or satellite service or mesh networking. We talked about a lot on that. The other scenario is we could use UAVs as to airlift base stations. So we call them as flying base stations or aerial base station. Of course, we know that there are many applications, things like disaster response, surveillance, remote monitoring, and all that. So this doesn't have a lot of material that we didn't know. We already know all these things. But now let's look into. Suppose you have a aerial base station. The question is, how do you move around? How do you move the vehicle around? Number one, that's called trajectory design. And the second is, how do you manage the resources? Here exactly what is the idea here? We are trying to place a base station on top of the or attach it to the drone, and then we want to move around the drone in a trajectory. Like for example, you could think of like a drone is making circles. That's one trajectory. We will complicate it later, but to begin with, so you have the flexibility to move around the vehicle. At the same time, the main purpose is to provide communication to the ground users. So that means we need to look into how do you provide the communication support for the ground users efficiently, in the sense maximize the minimum, use the resources optimally. So for example, what are the resources? When you talk about resources, what are the resources you are referring to? Power is one resource, right? And then of course, what is the second resource? Bandwidth, power and bandwidth. Those are the main things. And at the same time, you want to see where are you want to use those resources to provide connectivity for the users. So the topic is joint trajectory design and resource allocation. So how do we move the vehicle in such a way you are optimizing the resources? But keep in remember, before you even talk about optimization, our primary goal is to provide connectivity for the user. So how are you going to provide the connectivity? And to help provide the connectivity for all the users on the ground, how do you move around? So that is the thing. So there in the paper, the reference paper that I used suggested two techniques. One is orthogonal multiple access, second is non-orthogonal multiple access. So we know these examples, like for example, in terms of time or frequency or code. Time, with respect to time, good known orthogonal multiple access technique is TDMA or FDMA. The third is CDMA. CDMA is also very powerful. In fact, in CDMA, what are you going to do? You use codes. It's neither time or frequency. Maybe you can think of like a code. The codes will provide you a way to provide you multiple access, but they can be both orthogonal and non-orthogonal. Time division multiplexing is clearly orthogonal. Frequency division multiplexing also is orthogonal, but CDMA can be both orthogonal and non-orthogonal too. So many of you know what is orthogonality, but in simple terms, when you say TDMA and FDMA, you are allocating different time slots in the case of TDMA. In the case of FDMA, you're allocating different frequency bands. So orthogonality means they don't overlap. So for example, if I say, if I ask you your questions, then if somehow I manage to come up with a time slot for each person, if one person is talking, other people are not talking. So the focus is only on the one person, there is no disturbance, there is no interference. So that is called orthogonality. As long as we schedule time slots for each person, each user, then there is no overlap, and so we achieve orthogonality. The same way in terms of frequency division multiplexing, you are dividing the frequency, creating different slots, and you are allocating it to each slot, and there is no overlap. There is no, so that is the meaning of orthogonality. So here it says, if you use orthogonal multiple access for UAV communications, then what are the pros and cons? So we are looking into both cases, non-orthogonal multiple access, what are the pros and cons? But before we do that, what is the context? We need to really understand the context. The context is, you have a base station flying in the airspace, and there are users are on the ground. So typically, if the application is towards the application context is disaster recovery or disaster relief operations, then imagine, so let's take a simple example. Let's say you have a drone. Then ideally, the drone has to move to a place where the users are located. Now, if I keep the drone here, assuming there's a large area, and then people are distributed in different locations, because it's a disaster area. We are talking about emergency communications, and then people will be randomly will be located. And then the goal is to, if I want to provide service for the users, the key thing is go to the place where the people are. However, if the one option is just go around and then try to provide connectivity to the users. That's one option. Second option is figure out where the users are and go there. So it does this paper, the reference paper that I am using here, didn't go into that extent of identifying where the users are, but all it does is to begin with, it just makes a nice round and then connects to the users and gives using a time slot for that user, and then go to the next person, go to the next person. So to begin with, let's not even worry about going towards the users. Just imagine that you design some sort of a trajectory to begin with, a fixed trajectory, and then you're trying to provide connectivity to the users along the trajectory. That's a simple thing. Okay. Then we'll look at more advanced concepts. So while doing so, let's assume we are using TDMA. So what does it mean? You are looking at basically the trajectory contains a set of points, a set of waypoints, a set of coordinates, and when you are at a specific location at a specific coordinate, you connect provide connectivity to the user, closer to you, and then go change your position, again provide connectivity to the other user. So while doing so, you are assigning a time slot for each user. So whenever you are at some certain location, you are giving certain time slot, and then you are going around, and then while you are going around, because you are circling, think of like you are circling, coming to the same position. So basically, you can think of total time period is t, and then you are dividing by n number of users, and each user is getting a time slot of t over n. That is one approach. So keep that in back of your mind, and now let us understand how this orthogonal multiple access technique works. So first thing is, I already gave you the background. So based on that, you can say orthogonal multiple access technique allows a UAV to communicate with one user at a time. Allocating, it's possible that you can focus only when you focus on one user, you can provide as much power as you want. Okay, and this method ensures that users do not interfere with each other or with one another during the communication. Basically, you're trying to provide communication to one user at the beginning of the research, but practically it doesn't make sense. If there are n number of users in one area, you need to provide communication for all the users. You can't just pick one user among this group and say we're done, right? So for that to happen, you need to think about multiple access. This doesn't hold good. But again, to simplify the problem, the paper that I referenced, the paper I'm presenting, is actually saying that let's take one user at a time. So probably the context that they're assuming is people are spread around, and then you define a trajectory based on fix the trajectory, or even better, come up with a trajectory based on where people are present, and then go towards one user at a time. Okay, but this is okay. This is nothing. This is a simplified or a basic problem. The problem is defined in a simplistic sense, so that's fine. But the key thing is the benefits are, because it is possible to provide all the power, whatever the user needs. It's possible. That means you get users get high quality signal, and then the second thing is you don't have any interference because you're only focusing on one user at a time. Okay. Of course, as I said, this could be modified to provide, even though the vehicle is at one location, instead of focusing only on one user, it's possible to provide connectivity to multiple users. Then what do you need? During that time slot, maybe you could use frequency division multiple access technique to provide communication for group of users. Okay. So, but anyway, to understand the problem, to understand the concept clearly, it makes sense to think about a simplified problem. The second is power allocation benefits. Because the UAV dedicates all the power to one user, you get a good signal quality and reliable communication. It's particularly beneficial in scenarios with high user demand and limited resources. So there are a lot of users, but again, resources means again power and bandwidth. Think about, whenever you talk about resources, think about power and bandwidth. Given that, especially when you are airlifting a base station, depending on the what you call payload capability, how much weight it can carry. Maybe it's possible that that if you have only limited payload capability, then it makes sense to use low power, like for example 1 watt, and then you have a limited bandwidth. So that means your payload will be very small. So like something like a micro base station or micro cell tower, micro cell. So based on those criteria of how much the vehicle can carry, it makes sense to use limited resources. At the same time, you are going around, you are providing the connectivity for one user at a time. So that's the idea. Basically, this says let's focus on one user at a time. The examples are UAV can serve multiple ground users sequentially, ensuring each user receives optimal communication quality. In emergency response, UAV can prioritize the communication with first responders in a specific area. Basically, if you have a way to figure out where are the first responders, and then you spend more time where the first responders are there, and then if you still have resources, you go around. So this is at this point I think you can also think about some scenarios on your own. For example, so how do you handle this? How do you deploy a base station efficiently? Basically, how do you place? Where do you place? So I'll give one example, then you can think about other scenarios. In fact, practically, we are going to do a demonstration. We're going to do an experiment sometime this year, as part of what I call annual exercise with the city, where University of North Texas is located, is the city of Denton. We work with the city, especially with the fire department, to do some mock drills. We do some annual drills. So this year we are doing it sometime in September. We create a mock scenario. An example is this time what we are going to do, we are doing a chemical spill. We are trying to mimic a chemical spill on the road somewhere, and then given that disaster, we are preparing for the future. Suppose something like that happens. The reason why they picked up this topic is, or this scenario is, when you look around disasters, natural disasters or man-made disasters, this came up on the top. So many times large trucks actually carrying hazardous material, they're supposed to be safe, they're supposed to take care of a lot of precautions, but it's possible that accidents happen. So based on the history or historical knowledge, we thought that the fire department thought this is a good exercise that we could do. And as part of this, we also wanted to, because the project that I'm having, I'm running, we wanted to use the aerial base stations as an option. So we were thinking, what's the best way to make use, to deploy this or demonstrate this? So keep that chemical spill aside. With respect to chemical spill, a lot of other things have to be done. For example, one thing that we need to do is, what is the extent of the damage? Meaning that how much area we need to evacuate, for example. Because chemical spill means a lot of gases that are coming out. And again, there are many types of chemicals, so it's not just one kind. So in this case, we are actually deploying a drone and then attach a sensor, and then using a rope or some sort of a wire, we will lower the sensor while you are flying, and then we are measuring the what you call the concentration of the gases at different locations, and then and ultimately with the goal of figuring out how much area we are supposed to evacuate. That's a separate thing. Just we are flying a drone. There's nothing to do with the communications. The other hand, in terms of providing communication, which means that in that case if the existing communications are not working, or you are totally in a remote area where there are no communications are available and the first responders are going and helping the victims. In that case what happens, one idea is to just survey the whole area first and see where are the people, and then work towards deploying the base station at that location. See, that is the case, especially when you want to deploy a tethered drone. Okay. In this case, trajectory and joint trajectory and resource allocation problem, we are not assuming tethered location. Okay. So the point is, depending on what you plan to do, what you want to do, you have to have different approaches. So this approach is, in this approach, we are moving around, but it's not a we cannot keep in this case we cannot keep the drone for a long time in the airspace. That's a disadvantage. The other case is, if you fix the location, then you can use a tether to provide the power and also the network connectivity. You need both. Power allows you to keep the aircraft or the base station for longer time. So that means you're extending the airtime or lifetime. So for that to happen, you need a tether. That means you are providing power supply from the ground. It's possible. A lot of people have done that. The second is, you also have to provide connectivity. That means you have to provide a Ethernet kind of a wire or fiber optic wire coming from the drone all the way to the ground. So remember, if you go back and remember what we did in the first class. On the drone, you're only keeping some part of the equipment like radios, just a radio unit, or sometimes only antennas. On the bottom, on the ground, you are keeping the core. So if you think about radio and the core means you're connecting to the network. So which means that you need some sort of a fiber optic wire hanging from the drone all the way to the ground. Same thing with power. But if you do that, you cannot move around. So we are not discussing that scenario here. Anyway, so depending on the context, depending on the scenario, the deployment of aerial base station varies, changes. But in this case, we are assuming that you are able to move. So how do you move? You need to figure out where the people are located, okay, and which group of people need to be given priority. In one case, you can just go around and then give equal time for everyone. Okay, I think the paper that I'm discussing now and later is about, it doesn't prioritize, but it can be done, it can be prioritized. Maybe, for example, first responders could be given more priority and more time. So in general, what is the idea here? You are giving connectivity to one user when you are closer to that user, and then going to the next location, and then coming back. So these time durations are obviously not so small, meaning that you're not handling multiple calls, okay? So think about it. Normally what happens, suppose we are using TDMA and you are communicating with the cell tower. How does TDMA work? We are all talking at the same time, but you are giving tiny time slots, and you don't even realize that as a user, you think you almost got a dedicated line. But practically, the cell tower is giving you a very small unit of time at a given time, and then by the time it comes back, you don't even realize that you don't lose any connectivity. But here it's not the case. Here you're saying that each user is given a time slot. You get connectivity it's not in milliseconds or microseconds. You are given in terms of minutes, and then going around and coming back. Okay, it's not possible to combine to give you a millisecond here and send the drone to some other place and give you another millisecond. That's not possible because movement takes time. So when I talk about time slot, keep in mind that time slot is longer, not in minutes, not like seconds. But the point is, you can think of, okay, my total resources, obviously here, yeah, call duration is, you're limiting the time because, yeah, then you can, you will not, it's only for a few minutes and then we'll go to some, so suddenly, fix it also, yeah, maybe a few minutes. So the main thing is, time became a resource for us, even though we know that power is the resource and bandwidth is the resource, but in this case, time became our resource. So how much time you allocate? Because time is really a resource, because critical resource, because it depends on how long you keep the aircraft in the airspace. How much time you think a typical drone will fly? It's hardly 40 minutes or so. So it's not even an hour. If you can get an hour, or you want to really have longer time, battery is not enough. Typically these drones are powered by battery, but if you can power with diesel engine, and then that's different. Okay, we are not like for agriculture, for example, 30 minutes doesn't cut. If you want to spray some chemicals or fertilizers and all that, you need a lot more time. And if every 30 minutes you have to change the drone, that probably may not work. But here we are referring to battery powered drones, so which means that your time is extremely critical. Time becomes a resource. But the point is clear, right? We are trying to say that if you use orthogonal multiple access techniques, for example, if you use TDMA, TDMA, that then you are giving a time slot for each user based on the location and coming back. And the problem of resource allocation is also interesting. You will see in the second half, we will define the time slot very clearly. We will define the problem very clearly in terms of those variables. Yeah, I think this is good enough. We will move on to the. And then what are the pros and cons? limited user capacity. But the technique is TDMA or something like time. You're using time as a unit. Time is allocated or shared between users, or frequency, or code. But overall, it is still the capacity is limited. Then spectral efficiency refers to this is like a metric. Remember, sometimes you have to figure out what are your resources, what are the metrics that you are trying to optimize. So here, how many users you can provide. That's number one metric. Here the second is how much is the overall spectral efficiency. So spectral efficiency really refers to like bits per hertz per second. Okay, that's, in fact, if you look at the definition of Shannon's capacity formula, you will see you can say either bits per second, or if you divide by the bandwidth, then it becomes bits per second and hertz. So that is the spectral efficiency you are referring to. The other thing is there is a concept of maximum attainable sum rate. So what does it mean? If each user is each user is getting rate R, 10, suppose there are 100 users, you say R1 to R100. So sum rate means the total rate. So rate again refers to how many bits per second you are getting. So total sum rate refers to total sum rate. Yeah. Say again. Yeah, total capacity, or total the maximum data rate you are able to provide. Very good. That's correct. So these are the metrics. So it's also remember it's always important when you solve a problem like resource allocation. The key thing is what are the resources, and then what are the outcome, what are the output that you are measuring. So in terms of all these terms are the metrics that are useful. Some data rate or spectral efficiency, those are the metrics that you want to either maximize or optimize. Then this says orthogonality loss. Channel induced impairments can destroy orthogonality. What happens is, even though while you are transmitting you are using the orthogonal techniques, that means you are combining the user data in some sense in an orthogonal manner, but by the time it receives the receiver, you may lose the orthogonality. Can you think of a good reason why you use orthogonality? One of the reasons is mobility, because when you move around, suppose say, I think a good example is like suppose you are using orthogonal frequency multiple access technique. Then you packed your data in such a way that there is no interference between the symbols that you are transmitting, but a Doppler shift resulting because of the mobility of the receiver, especially like drones, you will see a frequency shift. So, or in terms of if you think about time, in terms of time, so frequency shift is caused by Doppler shift, but in terms of time, multipath will cause because of multipath you might lose the orthogonality by the time you receive, meaning that you are getting symbol interference. Frequency refers to inter-carrier interference. In terms of time, it is inter-symbol interference. So that will cause loss of orthogonality, and then you need to come up with some compensation mechanisms at the receiver. So I'm trying to give a simple idea behind each of these things. Okay, latency. Traditional techniques like orthogonal multiple access techniques we can introduce higher transmission latency and signaling overhead, meaning that when you switch from one user to another user, and then when you are suppose you give more time for one user, then other users will get latency. There will be delays because depending on how you allocate, for example, if the number of users are increasing, then that will cause latency. By the time you cover everybody and come back, you may have more latency. Yeah. So latency latencycy also is a metric, by the way. Latency is a metric. We talked about bandwidth and power being resources that you want to optimize, but what are we optimizing? One optimization criteria is one optimization metric is latency. So spectral efficiency is one thing, number of users you are supporting, that is another metric, and overall how much data rate you are getting, that is another metric. Latency is another metric, and you want to increase this, but you want to reduce this. That's right. And then scalability is an issue. Basically, we're looking at what are the issues we need to worry about when you are using orthogonal multiple access. Here, as the number of devices or number of users increase, we have scalability issue. In fact, anytime we design any technique, you always have to think about scalability. Scalability means what happens if the number of users increase, or if another idea is what happens if the area is bigger. So those are the scalable issues. It's not sufficient. We're not looking at a one-time solution. You need to think about how can you scale it. That's always the very important factor when you design a solution. Then one challenge is high mobility. Orthogonal mobility may face challenges and maintain orthogonality and performance. So mobility causes frequency shifts like Doppler effects, right? So then orthogonality will be lost. And earlier we talked about the other reason for what you call performance is the multipath. So especially when the drones are flying low altitudes, we get reflections from the ground. In fact, there is a tool called InSight, InSITE. Using the tool, you can model all this. You can model a terrain, and you can also put some buildings at different heights, and then and see how many reflections you are getting. Okay. Right, multipath is connected to intersymbol interference, and then frequency shift causes an intercarrier interference. All right. So these are the issues that we need to think about. But no, while we are looking at what should come to your mind is you should think about which of these are metrics, which of these are resources, right? And then which are these are the metrics that, and which are we need to maximize or minimize, and how do you put them together? Then the other option is non-orthogonal multiple access. In fact, this paper is, by the way, I didn't do work in this area, but the topic is of interest to all of us. And then the second thing is, I found a very good paper to discuss, a very basic paper that I will be talking about in the next second half. So I didn't really, basically I didn't give much importance to non-orthogonal multiple access, but there's a lot of work that has gone in this direction. For example, as I told you, CDMA makes use of codes, and the codes can be orthogonal and non-orthogonal too. Orthogonality assures that you don't see overlap, or that means orthogonality will make sure that multiple users' data is carefully placed in such a way that if the channel conditions are good, you will be able to, you won't see any overlap between the users' data. But if it is non-orthogonal, you're intentionally, by design, you are actually allowing overlap. Well, that's a very tricky thing, but people have worked on it for many years. So what happens is, why are we doing this? Number one, it allows you to increase the capacity or increase the number of users. Number one, that means, for example, let's say using code, normally suppose you have enough, so normally suppose say using orthogonal CDMA, only 4 users, only n number of users you can support. With non-orthogonal multiple access technique, you intentionally can add maybe double or maybe 125%. Instead of 10 users or n users, you can make it, you can have two times n number of users. So that is possible. The catch is, by design, you are mixing 1% data with others. Okay, let's understand that first. Okay, the second thing is, how do you handle this? Interestingly, there is something called successive interference cancellation. You need to come up with techniques to remove the interference. You are intentionally adding interference, and that is legitimate. It's not really it's not like unwanted data. It is data that is coming from multiple users. So, but by design, you are adding multiple users data in the same time slot or in the same frequency slot. But then the solution is that the receiver, you have to figure out how to separate. So for that, there are techniques such as successive interference cancellation. So I will only give some details. How do you do that? So one idea is you use different power levels for different users. So it seems like by playing with the power levels, you are assigning higher power to some users, and then change the power level and use a different power level for the other second user and third user, like or another group or other user. Let's call it like one user has P1, other user has P2, and in the decoder side and the receiver side, what can be done is, you first focus on the user with higher power, so detect that data, and then use that information to remove that data and focus on the second user. So basically, even though you are combining the data belonging to multiple users, it is possible to allocate different power levels, so that in the receiver, you start with detecting the first user's data with highest larger power, and then use that information to cancel that first user, and then so that you can decode the second user's data. So basically, variable power allocation and successive interference cancellation are the techniques to address or decode multiple users' data that is intentionally interfering because you are using non-orthogonal multiple access technique. Yeah. Okay. Yeah. Yeah, that's a good point, but my understanding is that what happens is, both of the powers will go through the same amount of path loss because they're going through the same channel, right? So it's not that they're going through variable power loss. So point is, so let's say transmit power is P or Px, Pt. The receive power is Pr. Okay. So you are combining two symbols. Let's say you are sending one symbol for one user, another symbol for the second user. Okay. So whatever path loss happened for the first user, because your idea basically the same condition, same scenario. The users they're not too far, okay, but maybe you are thinking the users are spread around. No, we're talking about the groups of users in the same location, like here. So the path loss that you encounter from the cell tower to your phone is practically similar for all the users. Okay, so the return power also. What I'm saying is, transmit power you are choosing. Okay, so for example, for you it is P1, for me it is P2. Okay, and let's look at the uplink. Maybe from here the data is going to cell tower. Cell tower has to figure out. So our data is mixed. One, we are not using orthogonal technique. So that cell tower has to figure out what is your data and what is my data. So the technique is successive interference cancellation. First the focus is on user with the higher power, and then using your information, we go back to the combined data and remove that. So they get my data. So, but what your question is, what if the receiver is receiving different path loss for you and different path loss for me. So what I am saying is, because we are in the same area, the path loss from here to the cell tower will have the same thing both for you and me. So path loss will be the same for both of us because we are in the same location. Well, not every place, as long as we are in the same, because we are in the same area. Yeah, not in different locations. So I'm not saying that if you are here and I'm some other location, that's different. But here maybe there is a little bit of confusion, because earlier I was talking about a user is given a lot of time, and then we are going to the second user. Here I'm talking about users in the we are focusing on a group of users in one location. Okay. Yeah, please. That's right. Right, yeah. So taking advantage of that, we came up with powers we can give it, so that the wrong signal will go to the border and the weak signal go to the buffer. That's true. So we use cancellation for the first buffer, and the second signal will not reach the boundary, so he'll get the last signal. So now, if we do this problem from a UAV, right, both are equally different. So this single power is not that simple. What we do at HQL and not HQL. It is true, but no, I think in your case also can be addressed actually. What the point he is making, right? Yeah. So, right. Yeah. So based on the power, the first user can remove the high power and get the synopsis. And the far away person may not have to do anything. He gets the because the weak signal will not travel up to him. Okay. So it's possible actually. No, there are right. Yeah. To begin with, yeah. So you're right. From that distance to the user, that circle is almost same. The angle is little bit of angle difference with them, but that is not sufficient for separation of signal. So can you still work with non-orthogonality normal? Yeah. In fact, we will go into a little more detail, but it is the point is you are using different power levels and then using successive cancellation is a well-known tale. It is possible. Yeah, but let's look into a little more, and then we'll come back to that point again. Yeah. So in this technique, you are employing power levels to separate users, facilitating simultaneous communication on the same frequency band. So whereas in the previous case, for each frequency band we are only allocating one user. The approach optimizes resource allocation because basically because of your maximizing the number of users, or you increasing the number of users. Yeah, but let me come back to the point again. Okay, later we'll discuss that in a and then there are also adaptive techniques. Adaptive modulation and coding schemes are employed to enhance communication reliability. So what does it mean? Adaptivity or adaptation comes into picture when the channels are in different conditions. So for example, I think Dr. Prakash was mentioning, if the user is far, then not only that you can adapt the power, you can allocate more power for the user who is far and less power for the user who is closer. You can also use modulation. Modulation techniques also can be adapted, right? These are also nothing new. They are also standard techniques. For example, if the channel isn't good, then you could use high data rate, like 64 QAM or more bit. Basically, you are sending more bits. The symbol, more bits per symbol. Whereas Whereas if it is the channel is of not so good, then you want to reduce the bit rate, data rate. For example, you can use QPSK or 16 QAM for reducing the data rate, and then if the channel is good, then use higher data rate. So that's what it means by adopting the adaptive modulation schemes. So you can change the power level, you can change the modulation technique to increase the data rate or reduce the data rate based on the channel conditions. So that is possible through this technique, through number. And feedback mechanism. Feedback mechanism is meaning that, let's say you are using, so it's also related to adoption techniques, because in the feedback you are going to get quality of service, channel feedback or service feedback. Based on that, you can change the data rate. So that those are possible. The other interesting thing is, in this technique, they say clustering is one technique and then user pairing. So the idea here is you are grouping users into groups, and then basically like you're clustering or grouping of users based on again the channel conditions. The idea behind that is, instead of grouping everybody into one group or randomly or fixing the fixing the channel allocation for each user in the same way, or fixing the time slot, for example, or you can actually group like pair or group, create a clusters of groups to schedule the time slots or frequency slots. So basically you can do more adaptation, you can try different strategies, as opposed to fixed strategy in the case of orthogonal multiple access. So once again, we are looking at different strategies, power domain multiplexing, or variable power allocation, variable grouping, and variable modulation techniques. So that kind of adaptation is possible with NOMA. Basically, here we are saying these techniques can be combined with UAVs, deployment of UAVs. So NOMA is also a well-known technique, but with respect, it makes sense to combine with UAV, because in the case of UAV, the adoption makes more sense, because as opposed to terrestrial communications. With UAVs, the channel conditions vary, and then you need to come up with ways to increase the efficiency in terms of number of users and then quality of service. So by design, UAV communication requires this kind of adaptation as opposed to terrestrial communication. There is basically what you're saying is, there is more need for adaptivity, more need for flexibility, especially for UAV communications. So it is, in general, NOMA is a better choice, because at the end of the day, with all these dynamic conditions, it makes sense to use these adaptation techniques to increase the overall efficiency of the communication system. So that is what this says. So this is a better fit. That's what you're saying, if you do it right. But at the same time, you will have problems, because we'll see in the next slide, there are some issues or challenges. It's not easy, even though in theory successive cancellation works, and then you can do all this, but practically there are challenges, and one of them is synchronization. We'll talk about in the next slide. But these are interesting techniques. These are interesting problems actually. There are interesting challenges, and problems are also interesting. Instead of just fixing the time slot or frequency slot, you're doing more than what, more intelligent or more, you're using some smart techniques, but at the same time, the solutions have to be designed carefully. So we already covered this. So because of the, by design, you're increasing the network, you can say data rate or network capacity by allowing multiple users to be served simultaneously. It enhances spectral efficiency, better utilization of available resources. Because really speaking, when you deploy a UAV, the resources are really constrained. You know, your flight time is hardly less than an hour. And then within those limited time, you're supposed to, you're actually doing a very critical need. You're serving a critical purpose, providing connectivity during disaster scenarios in tough times or challenging times. So we need to do as we need to develop smart techniques and intelligent techniques, and probably this is one such strategy. Okay. Now look at, I mentioned about device synchronization. This means because you are using it's not non-orthogonal, that means you are intentionally combining multiple users, that means you are dealing with multiple devices, synchronization becomes a challenging. In fact, we are not giving any solution, but we are only highlighting the challenges. So synchronizing the timing among devices is complex. Devices can estimate timing based on some historical knowledge. So maybe things like data driven techniques like machine learning techniques might help us to achieve these goals. Traffic estimation. The problem is interesting, the problem is challenging, but at the same time, these are the issues we need to think about. Accurate estimation of device transmissions is essential for effective resource allocation. If you want to increase the resource allocation, you're trying to combine multiple users' data, and then in order to separate, in order to extract that, you need to estimate the traffic. So maybe this is connected to these two are connected as well. Power control measures adjust received power based on the number of transmitting devices. So these 2 points are connected, right? Now you need to figure out which user is where, so that you can allocate power accordingly. So this more analysis is required before you design the technique. The sum rate or effective data rate depends on how many devices are transmitting at the same time band. So that requires us to develop some efficient techniques, or basically accuracy is important. When you are combining data, the synchronization, traffic estimation, and then figuring out how many number of this is also another important. Which users you want to group. We talked about grouping users before. Here also, which users you can combine. You are trying to use the same frequency slot or same time slot for multiple users. So which users you want to group, that is actually becomes important. In terms of solutions, one is successive interference cancellation. These are known techniques, but in terms of performance, in terms of applying in this context, you need to go into more. You need to look into that more in detail. Channel estimation, estimating channels for multiple devices is of course challenging, especially with if you are using multiple antennas, is even more difficult. So in general, the idea is not new, but in terms of implementing and figuring out how do you allocate the resources, and then how do you apply to this given context? I think that's probably challenging. Yeah. Sure. Yeah. So we just got the overview of different techniques and how they work and what are the pros, positives and negatives of the two techniques, especially orthogonal and non-orthogonal multiple access techniques. So we will wrap this up quickly and then get on to a small problem and get into more details. Okay, in terms of applying these ideas in the context of UAV deployment, these are the different strategies. One is, how do you place the UAV in general, and then if it is, even it is one UAV, the placement of UAV specifically in terms of at what altitude you want to keep, that requires optimization too. Deployment of even a single UAV, because on one hand, if you go higher altitude, it's better because you are getting a better line of sight. On the other hand, when you, if the same distance, the distance also will cause path loss too. So it's not that the performance is going to be monotonically increasing or decreasing. So placement of even a single UAV also requires to figure out what is the optimal altitude for overall performance benefits. In terms of multiple, when you have multiple UAVs, the problem is even more interesting. But obviously, you need multiple UAVs because one UAV may not fit or may not provide connectivity for a large number of users. So typically, one UAV or one base station can provide communication for certain area, and that area is not too large. It will be like few kilometers. And then if you want to increase the coverage, that means you want to increase the coverage area or increase or provide connectivity for lot more number of users, then you need multiple UAVs. So in that case, there are several publications I have seen. So it's always good to go look into the simplest problem. Look at a paper that talks about a very fundamental level and defines the problem in a very simple manner. So in one case, I read a paper where there is one UAV and there is one terrestrial base station, and one aerial base station. So how do you position the aerial base station in such a way that you minimize the interference from or between the two? So for example, if there is a user on the ground, a user using with his phone, then he may be getting a signal both from the aerial base station and also from the ground terrestrial base station. So the challenge is, how do you, at what height or what distance, both horizontal and vertical, at what horizontal distance and what vertical distance you want to keep the aerial base station so as to minimize the interference coming from the terrestrial base station, or minimize the interference coming from the aerial base station to terrestrial user. So imagine that there are two users. One is a ground user who is using the terrestrial base station, and then another user who is connected to the aerial base station. So the challenge is, how do you minimize the interference? And at the same time, you want to either in terms of increase the quality of service, minimize the interference, or you can, if you think about multiple users, how do you increase the number of users or the area of coverage, and keeping these constraints like power is fixed, keep the powers fixed, and then increase the coverage. So those are the things. So in simple sense, if you have either one base station or two base stations, the key thing is how far in terms of horizontal distance and at what altitudes you want to keep, that is a research question. So my suggestion is pick a problem, pick a paper that actually talks about the problem of placement in a very simple sense, in a simple manner, and then try to understand, then you can come up with your own solutions for new problems. So the third one talks about, so we started with one UAV, then multiple UAVs, and in general, if you keep it more, keep the flexibility and figure out if you want to look into 3D space, in three-dimensional airspace or three-dimensional space, how do you place multiple UAVs to optimally? So once again, you are looking at 3 dimensions. Here you probably you're only looking at 1 dimension. The only challenge is at what height you want to keep. Here two parameters, horizontal distance and vertical distance. Here if you have multiple UAVs, how do you place them in the 3D space to optimize the performance? So in any case, you need to think about what parameters you are trying to optimize, and what are the constraints. So you need to define them carefully to be able to address these questions. Okay. Yeah, I think we will close this after this slide. Yeah, in terms of what you call performance with respect to one user, these are the throughput and delay makes more sense. In terms of user, from a user perspective, for each user, how much data rate we can provide, and then are we providing the connectivity with the required limits of delay? So latency and data rate, those are relevant for individual user point of view also. So one thing is system performance, but at the end of the day, when you look at individual user point of view, these are the things that we can abstract. One is higher throughput occurs if the UAV is closer to the users. So what does it mean? It means that in terms of trajectory design, this plays a role. If you go closer to the user, then you can provide good connectivity and good data rate. So optimization of trajectory means how do you choose the position of the UAV and the users you are servicing in such a way that whenever you are providing service to the users, I think it makes sense to be closer to the users. So that means you have to basically move around closer to the users and then choose which users or which group of users you want to provide, and in that sense trajectory design becomes important. So the problem is definitely of valuable, meaning that it has meaning. It's not an academic problem, but it is also practically meaningful to figure out how do you design the trajectory in such a way that you are able to service users more effectively. That's a main idea. Yeah. So the other things are optimized trajectory positions the UAV on closer to the users. So I think this extends to this is an extension of the previous previous concept. So if you are the closer you are to the users, we are saying that you can provide better connectivity and better signal strength. So in some sense, a good trajectory design will increase both the throughput and delay. It will reduce the delay and then also increase the throughput. The other factor for the delay is that at what time you are going, how much time you are allocating for each user. So if you spend more time in one location, then you are delaying the service for other users. So I think look at the last bullet also, these two are connected. Choosing the right communication period is important because larger T will improve the throughput Larger T will improve the throughput, but also leads to longer delays for other users. So larger, how do you design the communication period, the time period is important, because if it is longer, you are able to give more time for some users, but T also is a round time period. Now how much time it takes for you to come back to the same user. So if T is larger, then the round trip time until you complete the servicing or allocating time for all the users will be longer, which means that the first user will incur longer delay to get the access again. So in simple sense, so I try to make this make sense of this. Larger T can provide good throughput, but it also leads to longer delays. Okay, so I will skip these slides, but let's get into a small problem. So here I don't have slides for that, but I'm going to use a paper I found very important and very valuable. So this paper, I chose this paper because it starts the problem definition or defines the problem from scratch. And this is also a good example for students to see how do you define the problem, even though at high level, okay, the problem is about trajectory design and resource allocation. But the key thing is where do you start? This paper actually talks from the fundamentals, explains using fundamentals rather. It explains how do you define the problem very meticulously. So that's the reason I picked the problem. So pay attention and see whether you're able to learn the technique and apply this for your own problems. Okay, that's the reason I chose the problem. So with the setting I provided the context. We understood why the problem is significant, why the problem is important, but now look into a nice design from basics, and walk with me and make sure that you understand every term, every variable that we are talking, so that way really you can appreciate. The problem is once again the same problem. How do you fly the drone so that you can provide connectivity for the users on the ground? Okay, so that is called joint trajectory and communication design. So you're designing the movement, how the pattern of movement. At the same time, you are saying how do I provide connectivity for the users. Okay, so that's the meaning of communication and trajectory design, or joint communication and trajectory design. So let's look at this. So to begin with, you have to remember all the variables, okay? Because it's like it's not too complicated, but there are about 10-15 variables. Okay, so try to remember the things that we talk about. There are to begin with, you are deploying a UAV as an aerial base station, and you are serving up to K users, capital K users. Okay, so the user set is they use a different letter. This is, by the way, a good notation. It's also, you can also learn how to create a good notation too. Capital K is different. This italic K is like a set. So K is a number. For example, K equal to, let's say, 10. And what is this K? This K is 1, 2, 3, up to 10. That's like a set. And then size of set is K. So that's how, very standard technique, but I want you to just pay attention and then follow this. We are using TDMA technique. So that's a orthogonal technique that we are using. And then we are assuming that the UAV serves the ground users via a periodic cyclic time division multiple access with each period cycle of T, capital T. So total time is T, but that's exactly what we are referring to in the previous cycle. If T is very large, it's good, you can get more throughput, but at the same time the round trip time is, the cycle time is, if it is large, that means some people will, while you are serving to one person now, the other persons will come later. So T, you have to choose the time. So it's also an optimization problem. How do you choose the time based on some constraint? But in general, we are using K users are there, and the time period is T. And then right here it says the choice of T has implications. On one hand, larger T provides more time for the UAV to move closer to each user. So if the T is larger, then it allows us to move the UAV closer to the users to achieve better communication channels. And if T gets sufficiently large, that UAV flying time is practically ignored. That means you are trying to say T is almost like closer to, and you can T is up to infinity or a very large number, then practically you are saying the UAV can stay stationary above each user. So it's possible that T is very, very large, then it's possible that you can model in such a way that you are getting a good line of sight. You can read this paper later, but we'll move on to get the big picture. If larger T also incurs larger access delay for users, since each user may need to wait for a longer time. Okay. So obviously there is a need to think about what is the right value of T. All right. Then we define the location of the coordinate of the user is Wi. So user I is located Wi with a 2 coordinate system. The reason we are ignoring the third coordinate is the altitude is fixed. We fix the altitude to like capital H or some fixed number. So practically we are looking at the 2-dimensional 2D space. Yeah. So the UAV is assumed to fly in a fixed altitude above the ground, and the location of the UAV is at a time t, at a given time, is q. So basically follow this, q defines the trajectory. So q of t is a trajectory, wi is the location of the user. So if it is a trajectory, then there are several points, like, so q has to be a vector. Or in other words, let's say at time t equal to 0 is q0, at time t equal to 1 it is q1, and at time t equal to capital T you are coming back. So q0 equal to qt because it takes cycle time t to get back to the same location. So basically you are making a round trip. Does that make sense? Right? q0 equal to qt. The reason is, after noting that q is the location of the drone, and q0, q1, q2, q3 and qt, capital T, will form a trajectory of the vehicle, and q0 equal to qt because you are making a full round. So what does it mean? In time t, capital T, you are making one round, one like, right? So that's how you need to think about it. So if you want to visualize, so here is a scenario. You are taking capital T amount of time to go one round, which means that you are making some sort of a cycles. Okay. And then he says q dot refers to is the velocity. Qt is the position, q dot is the velocity, and then we are saying that the velocity is upper bounded by V max. Yeah, so equation 1 imposes the constraint that UAV needs to return to the initial location by end of capital T. Okay. Okay. So there are not too many variables. I think if you are following me, you should be fairly able to fairly understand the problem. My goal is to review this so that to learn how to define the problem. For example, how to define this joint trajectory and communication design. How are we defining? And started from scratch. There was nothing. We're not using any predefined things. The description started from scratch. Okay. Now another interesting thing is, instead of keeping this trajectory like in a continuous manner, you are discretizing this. So try to follow this. Yeah. So the trajectory Qt can be approximated by n two-dimensional sequence. So instead of keeping t, which is continuous variable, now we are discretizing. And those who have taken signals and systems, they are familiar with continuous time signals and discrete time signals. But if you haven't taken, then pay few minutes of attention, then you will be able to get. So instead of, now earlier it was q of t, but now we are saying qn. What's the difference here? Qt is a continuous time and qn is a discrete time. So now the locations are changed to x of n and y of n. Instead of t, we are moving to n. Same thing. Basically, 1 and 2 are transferred to 3 and 4. q1 equal to qn. And what is this? Qn n plus 1 minus qn. What does it mean? N is the location at n, and this is n plus 1th location. And the distance between the two. By the way, these are the locations of the drone. So you're taking two instants, n and n plus 1, and the distance square is bounded by s square. S is the distance basically. So the distance between two locations, two successive locations of the UAV in the trajectory is s, upper bounded by s. So which means that s max, maximum of s, depends on the velocity. Distance equal to speed times time. Delta t is what you call time interval, slot length. Yeah, slot length is delta t, and then V max is the max. So the distance traveled by the UAV from instant n to n plus 1 is bounded by s max. All right. Then, assuming that all users' locations are known, how are we representing users? Wi. Ith user is located at Wi. So now look at this. You should be able to visualize, but if you have difficulty, let me know. This is important, where this is coming from. Otherwise, so spend a minute and follow me. So what is the distance from the user, from the UAV to the user? What do you think? It is like a diagonal distance. So for example, I think let me give some. So let's say UAV is here, and the altitude is h. Think about this altitude is a capital H. That's a capital H. Okay, and qn is at nth instant. Where is the drone? Suppose the drone is moving from along this line, and this is h, and the location is, what is the location here? Q of n. Okay, so that is the location of the drone. Of course, drone can be anywhere, but height is h, This is the location of the drone and this is the location of the user. So h square is the altitude. You can imagine, you can think Qn and Wi. Wi is already on the ground anyway, because the user is on the ground. But Q also is a two-dimensional length. So for example, if the drone is here, you are looking at the corresponding location on the ground. Okay. So user is, let's assume that let's say user is here. User is Wi, and let's say this is the location of the drone, but drone is not on the ground. It is at the same location, xy location, but with a third at a height of h. So convince yourself that distance between the user and the drone is this. That this is like a height, which is vertical distance, and this is the horizontal distance. So square root of that horizontal distance and vertical distance will give you actually the diagonal distance. Right? Make sense? Right? Yeah. So D is the, so see how nicely we build a simple setting, and then we are able to construct from scratch. Okay, now we can move a little bit faster. Yeah, for simplicity, we are assuming there is a line of sight, so we are not worried about non-line of sight, multipass, and all those. We can add them later, but to begin with, you need to take a simple model. And then even though there could be a Doppler effect, so what is the effect of, what is the Doppler effect? Because the drone is moving, you may see shift, frequency shift from the transmitter to receiver, but we are saying that techniques, there should be some compensation, but it's already, we are assuming that it can be addressed, it is addressed by the receiver, so we are not worried about it. Okay. Now, there's another interesting thing, especially if you haven't seen this before. Channel power gain, channel gain. This is we need to know for, because user is communicating to, there is a transmitter and receiver. So at the receiver, to compute the received power, you need to know what is the channel gain. So that channel gain is, it is defined slightly differently, but this is also common in the literature. It's saying the channel power gain from the UAV to user I during slot n follows a free space path line, because we are ignoring any multipath and other effects. So how are we defining? HIN for ith user. I stands for ith user. N is the time slot or slot n. It is defined as rho 0 times distance power minus 2. So di, we saw the distance. So basically, what is the path loss? It depends on d. And rho 0 denotes the channel power gain at a reference distance of d0 equal to 1. So this is one way to look at channel path. Path loss. Path loss is the function of normally frequency and the distance. We kind of abstracted out the frequency part. How do we do that? Just simply say, let's consider a reference distance of 1 meter on the path loss. The channel gain at a reference distance d0 equal to 1 is given by rho 0. So what happened to the frequency? It's embedded in this. Okay. So with having the reference as rho 0 at a distance of 1 meter, now we can say the channel gain for a different distance, because distance between the UAV and the user will vary. So and that distance is d sub I. So you can use rho 0, which is a reference channel gain, to estimate channel gain when the user is at a different distance. Again, I think it should be, if you haven't seen this before, you can talk to me later, but this is also a standard definition. So in this scenario or in this representation, D is known. So all we need to do is HIN is given by rho 0 over the distance we just computed. That's what, this is the distance. Because we are talking about distance square, you can get rid of the square. If you want, actually you can also open this on your screen if you can access, but otherwise when you go home and you can read. I just want to give you the gist of, and then what is our intent here? Our intent is to see how we are solving the problem, how we are defining the problem. In fact, solution is we can worry about later. How are we defining the problem? How are we defining the joint trajectory and communication problem? Okay. So that is the intent, and it's a good paper, very good paper, and in fact I know the people, I know the authors very well. Okay. Now, so we understood channel gain, and why do we need why do you need channel gain? Look at this. Your data rate or achievable data rate is given by Shannon capacity, Shannon's capacity formula. So capacity is nothing but maximum achievable data rate. So basically it is a C, it's a capacity equal to log 2 1 plus SNR, right? What is the formula? Channel capacity is given by log 2 1 plus SNR. So what is SNR? By the way, it's SNR at the receiver. So we are assuming that P is the transmit power, HI is the channel gain we just talked about, and then sigma square is the noise power. Okay, so this is signal to noise power. And then what happened to B? We are talking about, we are looking at bits per second per hertz. So B is not required here. And suppose if you put B, then it will give you bits per second. Okay. And of course, this is the definition, and then if you substitute for HIN from equation 6, you get this. And there is also another parameter we are introducing, gamma 0. Gamma 0 is P times rho 0 by sigma square. So there is a rho 0 here, and then we have sigma square. P is the transmit power. So this is easy to follow from this equation 9. So point here is, why are we computing channel gain? In order to get signal to noise ratio. And do you see, we're not considering any interference because you're using like a TDM mapping. Okay, if you consider interference, what will happen here? You will have signal to interference plus noise. So we don't have the interference here. So the beauty is very simple problem definition from scratch. That's the reason I like this and I wanted to discuss with you. Okay, then another interesting thing here. This needs a little bit of attention. So saying define a binary variable alpha in, which indicates that user I is served by the UAV in time slot n if alpha n equal to 1. So what is it? It's a binary variable. You are defining a variable called alpha, and then says you are saying alpha I n equal to 1 if user I is served in time slot n. So it's a once again, the reason I am bringing it up is to explain how you are actually bringing users into the picture. If user I is being served, then we are saying it is 1, alpha n equal to 1. So you look at time slot 1, let's say n equal to 1. If n equal to 1, you are looking at alpha I 1. So at a given time, by the way, at a given time you are only servicing one user. At a given time you are only servicing one user. So if alpha 1 of 1 equal to 1, that means alpha 2 will be 0, alpha 3 will be 0, and nobody else is being served, only one person at a given time. So n is this I is the user, subscript is the user, and what you have in the parenthesis is the time slot. So at any given instant, obviously one user is being serviced. So how does it go? Let's consider time slot 1, n equal to 1, and suppose first user is being serviced, then alpha 1 of 1 equal to 1, and alpha 2 will be 0, alpha 3 will be 0, and all that. So because only one user is being served. So take some time to appreciate this, okay. So with 3DMA, at most one user is scheduled for communication for each time slot. So what does it mean? If you look at all the users, k is the total number of users. I equal to 1 to k. If you sum all this alpha I n for a given n, it will be at most 1. If nobody is being serviced, it will be 0. But if you, of course, maximum one person can be serviced. So one of the i's, it will be 1. For all other i's, it will be 0. So the summation is at most 1. Okay, I know that probably it may not be so clear, but once you go home and review this, take this paper and read, you will be able to appreciate. So suddenly see, now we are able to talk about trajectory, because Q is giving the trajectory, and you divided the on the trajectory along the trajectory, you divided the into slots. So in some sense, we are saying even though the drone actually moves continuously, but we are assuming that the drone is at this location at n equal to 0, it's going to jump, almost like jumping to another location. So when you do the discretization, you're only fixing the locations. But normally what happens, drone has to go from location 1 to location 2, but that's not what we are saying. We are considering discrete steps. That's the way we converted from continuous time to discrete. The second thing is we are able to go all the way up to signal to noise ratio. By defining this, we defined channel gain, and then we computed the signal to noise ratio, and then we are able to get to data rate. So why are we getting data rate? Because that is the data rate is our outcome. We want to optimize the data rate. So that's the reason we are getting into R. So in 9 equations or 9 steps, we are able to consider the trajectory, right? And then from a communication point of view, when you say joint trajectory and communication, what do you mean by communication? Your data rate. What data rate you are providing for the users? So by the time you finish 10 steps, we have already defined all the variables that we need. Okay, so our goal is to only to define the problem but not the solution. Okay, so now the problem formulation. Okay. So A is alpha IN. So literally speaking, what is alpha IN? You are referring to the users. A is a set of your it's set up. A refers to, A is a function of, or A refers to the users. Alpha, if you set I equal to 1, you are referring to, if alpha 1 of n equal to 0, that means that user I is not being serviced, but if alpha 1 n equal to 1, it means that user 1 is being serviced. So A refers to the users and Q refers to trajectory. And not only that, indirectly alpha is referring to data rate, because if the user is given user is being serviced, then how are we measuring what are we measuring? What data rate? Alpha times rate will give you the data rate. For example, Ri equal to alpha I times, actually this is total lot, not Ri. No, so R equal to, you can say R equal to alpha times Ri. So interestingly, from n equal to what is n? Capital N, capital K is the users. What is capital N? Is the time slots, total number of time slots. In a total time period is capital T, and you are dividing into n. So for the entire round, by the time you make one circle or one complete circle of the drone, which means that within the one time period, you are servicing all the users, that means k number of users. But here in equation 10 you are only focusing on data rate for single user. So it seems like a little bit confusing, but if you read couple of times you will be able to make sense. These are all written very well actually. So Ri refers to data rate for user I. So now what about total data rate? Total data rate will be, you add for all the time slots. So this is for okay, let's look at this is the okay, let's look at little more clearly. So A refers to the users and data rate, Q refers to the trajectory, and the goal is to maximize the minimum average rate. So what we are trying to achieve here is focus on first the minimum average rate. So what is the minimum average rate? It is to do with the Ri. And what are we doing with it? We are trying to maximize the minimum average rate. That means something like a fairness. You want to make sure that every user gets at least the minimum rate. So in other words, you are trying to maximize the minimum data rate. So that is, suppose eta is our minimum data rate. You are saying the data rate has to be greater than this. So n is eta is our minimum data rate for all I. Okay. And what is in our control? You are jointly optimizing the user scheduling. So in some sense A refers to user scheduling, and then the trajectory is given by Q, and then the optimization problem is define a function. First of all, defining eta, a function of A and Q. So this is still abstract. Okay, we'll simplify it in a couple of minutes, and define this as a minimum data rate, and you are trying to maximize the same. If you define minimum data rate as a function of A and Q, which we already did, this is already defined in terms of trajectory. This is also already defined in terms of trajectory and data rate. One more second. Yeah. Yeah. So once again, A is the scheduling and Q is the trajectory, and the scheduling refers to how are you assigning, which user is assigned to which time slot, and then Q is clearly the trajectory, and then you are defining a function eta as a function of A and Q, and that gives rise to minimum data rate. So this is the data rate, and now you are saying how do you define both? You are defining both A and Q, scheduling as well as How do you design the scheduling as well as the trajectory such that the data rate is at least eta. So anyway, that's a simple way to, that's a simplest way to define. But again, this paper is publicly available. I would like you to take a look and see whether you understand. So now, this is how the formulation, the optimization problem is formulated. Yeah, hopefully it made some sense. I know that it's not 100%, it's not easy to follow a paper in 10 minutes or 20 minutes, but at least you can see, you're able to see how we are able to start from scratch and define trajectory, defining a scheduling algorithm, scheduling strategy, and ultimately you're defining what is the optimization problem in terms of data rate. And then if you read this paper later, you can see that this problem is not easily solvable. So let's look at one more minute. So let's start about, we spent a lot of time on this data rate. So this part is sort of clear. So this is a signal to noise ratio, and log of 1 plus SIR or signal SNR will give you data rate, and alpha I is is 1 for one of the users. If you're talking about user I, alpha 1 or user for alpha I n equal to 1 only for one user, or maybe in other words you can say for a given I, for a given n, it could be 0 or 1. That's how we defined alpha. Alpha is like a binary variable. So now the reason I'm describing that is, you look at this part. What this is saying is, at most for one user, this value is going to be 1. Out of k users, only one of the users will be scheduled at a given instant. So n is the time instant. At a given time, our problem formulation is, at a given time only one user will be given the communication link. So that means, so that is the key to understand this. How come for all the users, you are adding up all the users and you are saying the maximum value is 1? Why is that? Because only one user gets a chance, and sometimes maybe nobody is being serviced, then it becomes 0. So that is how you need to understand. So alpha is a binary variable, 0 or 1, okay? And then only one user gets a chance, and sometimes there is a chance that nobody is given service. In that case it becomes 0. So the point is, this summation for all, if you add up to all the users, is going to be at most 1. That is the way we are defining. Okay, once again we'll wrap up in few minutes. What is h? Is the altitude of the drone. What is qn? Trajectory in nth time slot. What is w? Is the user location. And what is this part? This is the distance between together actually. If you look at the denominator, it's the square of the distance between the drone and the user. And then that basically your signal to signal to noise ratio depends on the distance, of course, right? Say again. Right, in this case, but so that's a good point. But trajectory is defined. Yeah, trajectory is defined. So we are not. Yeah, in this problem, in the first definition, in the initial phase, the trajectory is defined. Yeah, but later actually you'll see. Okay, maybe the way you can think about here is, yes, trajectory is defined. Now at what time which user is being serviced? That is the problem that we are looking at. So once again, I think that the problem is well understood, because you're saying if I fix the trajectory, that means you have n time slots, and then now the question is, in which time slot which user you want to provide service. That is the problem we are looking at. Yeah, so you cannot move, real practically speaking, you are building up the problem slowly, you know, this is the beginning. The point is which user are you servicing at a given time. So obviously, you know, to think of it, what is the common sense logic? If you are at a location at a given location, see, once again, remember, you know, it's very difficult to start with a complex problem. You know, you start with a simple thing, and then even for the simplest problem like this, the argument is you can't solve this. So what the solution that they are the others are suggesting is, look at this. It is challenging to solve because first, this term that you are going to see, we are using in terms of data rate, it's not really what you call, it's not a convex problem. So now what is mean by convex problem? Convex problem is if the problem is convex, then you can find the maxima and minima. Otherwise, if it is like some random thing, you know, a random curve, then you cannot. So, local minima, yeah, if it is, yeah, but yeah. So what they are saying is, as we define the problem, as we define, the problem is defined something like this. Sorry, I think I should go back. Yeah. The problem as defined, this term is non-convex. So you can ignore log also. If something is convex, log also will be convex. So you can skip log for a second. What I am saying is, if a function is convex, log 2 of that also will be convex. But problem is this term itself is not convex. Because it's not convex, you cannot find you cannot optimize. Optimization is not easy. And then, so it gives a solution. Anyway, let's do a quick summary. The point is, we define the trajectory, even though it's, so now he says, yeah. So I'll leave it with a good punchline. How they're able to solve. In one case, he says, yeah. Yeah. We'll take about 5 minutes or no, less than 10 minutes actually to wrap it up. Okay. So he says, for a given user scheduling A, that means A is fixed, the trajectory Q can be optimized. So let's fix the A and then focus on the trajectory. So what do you mean by fixing A? For a, yeah, we are splitting actually. So for a given UAV trajectory, sorry, fixing the Q. The first approach is we'll come up with a scheduling strategy given the UAV trajectory is fixed. So how do you do that? Instead of this problem, now we are saying maximize the minimum data rate. So what is eta? This is the minimum data rate for all the users. So yeah, so the problem is now for a given trajectory Q, maximize eta. So maximize eta such that this term, that is alpha I times Ri. What is alpha I times Ri? So this is nothing but Ri, by the way. So here this is also Ri. Ri is given as log 2 1 plus SN naught. So this term is this entire term, log 2 term is Ri. So this is basically the same. This term and this term are the same. But now you fixed Q. So in the original problem, you're trying to modify or trying to find what is Q and what is alpha I. Or alpha I refers to scheduling. Qi refers to, or Q refers to trajectory. So we are trying to say for a fixed Q, maximize eta. So now he says, so once again, it may not be 100% clear, but we simplified the problem by saying, let's fix Q and then focus only on the, focus on alphas. So how do you choose the alphas? The question is, how do you choose the alphas? What does it mean? Which user you are going to service? And what is the answer? Really speaking, logically, what is the answer? Whoever is closer to the drone. If you fix the trajectory, then the answer is kind of straightforward, but in terms of the definition of the problem, find alpha is given Q is fixed. That's what this says.
Minimum channel is required for every minimum data rate required for a user. Suppose if it is a voice call 64 and that is
Eta is the minimum data rate. You're right. Right.
For if we have n slots, n into that eta, we are trying to find it out.
Right.
And we are trying to pick up the best user who can use that.
Right. That's true. Yeah. So basically, we're not bringing. There is no queue here anymore. There is no queue. It's only n slots are there. Yeah. Yeah. Minimum data. And in fact, the answer is going to be pick the user who is closest. That's the answer. Even though it is not discussed here. Yeah. Best user. Yeah. That's right. Whoever is the closest. Yeah. Right. Yeah. And now he says the other way is fix the scheduling. Given the scheduling, then figure out the trajectory. So see, the beauty of this is very basic problem, and normally even before I read this paper, trajectory optimization and communication, it seems to be very complex. You're trying to say, how do I design a communication? Broad communication. The term is broad, and the trajectory also is broad. But now we are saying, let's use what you call. Yeah, you define a trajectory in terms of locations. H is fixed, just only it becomes a two-dimensional thing. Right.
So you can increase the number of users in each slot.
Right. Yeah. In fact, yeah, right. In fact, here they say only one user at a time, but two users. Right. Right. Yeah. So the reason I picked this topic is because I wanted to show you. Even I also learned a lot, but primarily, how do you design a problem from scratch? That's the thing. Okay. Yes, yes, yeah, right, yeah. Yeah. And this person is the author, sir. He is a very experienced, very well-known professor, and the first author is probably graduated in 2018 or 2020, and then I personally know both of them because recently. Yeah. So I met them in person. Also, yeah, I know them. I had some conversations before, not in a different context. I didn't see when I saw this paper and then also like the paper, the way they wrote. It comes. Yeah. Yeah. All right, let's stop here. Okay, so what did we do in the first half? We learned about the general idea of trajectory and then what kind of techniques we use, and orthogonal multiple axis and non-orthogonal multiple axis. We learned the pros and cons, and we didn't go into any topic in detail. But I think by picking this topic, how you can turn a big problem into some baby steps, the small problems. So that is the intention. Okay, hope you understood the thing, and then of course, depending on what you want to do, and if you pick up this topic, or maybe continue. If you want to do something in this direction, then start with this paper, and then maybe there are many papers actually. There a lot of work has been done in this, but all of them are theoretical, really. Very best, yeah. And notice that it was in 2017. So over these years, probably practically not much work has been done. For example, as I said, even 2 base stations flying in the air is not done, and probably that's the reason I got the project. My project is deploy 2 base station and practically that's my charge. I have 2 more years or maybe 3 years to do that. But in terms of research, what you call research is different and deployment is different. In terms of research, you can think through and come up with some theoretical problems, but practically to implement this in practicality, yeah, you need a lot of resources. Yeah. I mean, you need to work with service providers, and you need to work with FCC. It takes more efforts. Yeah. All right, let's stop here. Thank you.
Okay, don't upgrade, only just update, right? You just try to update it, and if it asks for upgrade, you skip that command. Yeah, type the password. Okay, so once you update it, you install NS2. It takes few minutes for installing NS2. And once you install NS2, you have to install NAM. It is a network animator where you can visualize the
nodes and graphs, everything, the movement of the packets, right? And once you do that, you have to install TCL, because the language what we try to use for programming is TCL codes. Right, the first command is sudo apt -get update, and once the update is completed, you can run the second command, sudo apt-get install ns2, and once ns2 is installed, you can have the NAM installed, and this is Network Simulator 2, and 3 is available for modified versions of it. You can do a lot of programming in that for various latest technologies. And you have to include a TCL interface so that you can write or compile your TCL code on it. Okay, so at the window prompt, you can just type NAM and see how you can visualize it. No, it's not happening. With the dollar command, you can type and see. Okay. Okay. అవలేదు ఏమవుతుంది you have to repair it, okay, or you have to shut down it. Go to Ubuntu, there is a second line for manual operations. You have to pick up the second Ubuntu and give it and repair the dpkg, dpgk. Yeah, right. So I'll just try to tell you a small tutorial on Network Simulator NS2, what actually it does, and this is one of my friend Hemant Kumar Rath. He has developed this tutorial, small tutorial, and we'll be using that for explanation purpose. So if you try to see, it is a discrete event simulator, actually meant for studying the different networks. It is not for R&D, but it is for understanding the concepts of how the network can be simulated and be used. So in this, you can see that there is a protocol design. You can design some protocols, and you can also see at the same type the traffic, what is the traffic flows, and all these things you can monitor it. And you can use the data and put it to a graph sheet, or there is a traffic analyzer. If you give it, it tells you what are the different packets moving on the network and so on. And you can use it for both wired and wireless, but the wireless part is limited in this case. If you move on to NS3, there is a lot of wireless section built into it, right? Even satellites and IoTs and ad hoc networks, everything is built into it. Cellular, everything is built into that. You can pick up whichever you want it, right? So the back end, if you try to see, we can write the C code and it can run, but mostly the front end is only OTCL, the OTCL language, TCL language we try to use for writing the codes and all. And this is open source, there is no license required, freely distributed, you can use for whatever you want. And you can share codes, share the protocols, everything you can share it, okay? So you can, as I told you, you can simulate the both wired and wireless, but right now we are not interested in wired networks, we are mostly using wireless networks for our codes. So we are trying to see how to run a ad hoc routing protocol like DSR we have studied. Similarly, AODV is also a similar type of distance vector router. And in DSR dynamic source routing, we have seen it is a reactive type. Whenever a node wants to communicate, it tries to find a path and reach to destination. And here also it is same ad hoc routing protocol and ad hoc on-demand distance vector routing. So AODV means, so on demand whenever it wants, it finds the route and it goes. So both comes under reactive only. Whereas the advantage with AODV is, it can be scalable to 10,000 nodes, 20,000 nodes and all. Whereas DSR is limited to a small number of nodes, okay. So you can also simulate the sensor max and all, not only the high-end nodes like Wi-Fi and some Bluetooth and the other networks. You can also go to a lower end where energy is a constraint. That part also you can see. So the power control in wireless networks is the main important thing in sensor network. So you can adjust the powers and all in the network and see to it. And apart from this wired or wireless, you can trace and visualize the network also. What is happening inside the network, how the packets are flowing, everything you can visualize it. That's the added advantage of it. And analysis and all, you have a software called as Wireshark. So you can transfer this data into that and you can visualize everything, analyze it for your application, right? So once the data file is created, you can put it into another software like Wireshark or some graphical package. You can plot whatever curves you want and you can understand it much better. So if you try to see the functionalities, the traffic models, there are a lot of traffic models are there, but NS2 has a limited library, like it has web, FTP, Telnet, CBR, constant bitrate. CBR is a constant bitrate traffic and real-time traffic also, which is a variable one, right? So coming to transport protocols, we have the most popular one is TCP, what we are trying to use for our existing IP network, and you have UDP also where we try to use it for control packets, right? And multicast is also there. So if you try to see this Reno, New Reno, Vegas and all, the TCP, we have no topic of TCP in this course, but basically all the communications, if you try to see on internet, it is TCP based. We call it as TCP IP network only, right? So there are different versions of TCP available. Like if you try to see the first Reno algorithm, it is a slow start algorithm. So you start with transmitting one packet. If you get back the response in time, you increase it to 2. And if you get back the response, you increase to 4. And if you get back the response within time, you increase to 8. You go exponentially increase. We call it as a slow start. We don't start with full capacity and drive it, right? And if there is a congestion, again fall back to 0, again start 1, 2, and so on. So suppose you have incurred a traffic at 48. It doesn't mean that you have to start from 0. So you can start from half of that value and can start. We call it as a fast start, right? Slow start with fast retransmission. Instead of coming to 0 and again going up to 48, you can come in between 24 and you can still go up to 48, right? So this is what the modification in New Reno is, and so on. We have a lot of modifications came up, okay? So how to drop, how much to drop and all. There are a number of mathematical equations and people are trying in different formats and getting that. And those are the versions which you can see TCP, right? So then you have routing and queuing. This is primarily the main important thing where we have to concentrate. Like when we want to send a packet, if you start just transmitting at a high speed, the other node might not be interested in taking your packets. So these packets have occupied the network, but the receiver is busy. So you are not only doing a fruitful communication, you are blocking a path for the others to use it, right? So we should send the packet such a way that when it is ready and whatever it is speed, that much only we have to send. So there is a queue being generated, and the queues can wait until the receiver tries to receive it, and then you can release the packet. So if the packets are full, the packets will drop off, right? If there is a queue and if more number of packets are coming than the capacity, it cannot hold, so the packets will be dropped. So here in these networks, you can see the packet drops, packet loss, acknowledgements, everything. You can visualize it and see how it is going on, right? So in the queues also you have different types of queues, right? First come, first serve, drop tail, tail you drop it, head you don't drop it. So there are a number of ways you can implement it, and you might have seen in the microprocessor memory management also how the inputs are going and coming out, and read and write you are doing and all this. So in this physical medias you have wireless, and you have the multi-path propagation models also, right? Various multiple propagation models are there that we are trying to use, and even the satellites are also, you can extend it to satellite communication also. So you have to download the NS2 and start creating the topology, execute the script and so on, okay? So you can download for whatever version you want. You can put it on Windows as well as on Linux. In Windows you have to create a virtual machine and then put it on top of it, or you can have partition of it without disturbing your Windows. Your Windows will not be disturbed. Only thing is, when you start loading the Windows, it tries to adjust the memory, right? How much hard disk you want, how much you want to program, and so on. So, but you please remember that a minimum of 4 MB space is required for your NS2 only, and you need extra space for working also. So generally we ask you to put 10 GB or 20 GB as a partition and load Ubuntu on top of it, okay? So please keep in mind that whenever you want to do partitioning, minimum of 20 GB, you keep it as for Ubuntu purpose. And there is one command called swap. While installing it, asks how much swap you want. That is nothing but corresponds to the RAM, okay? So keep that as maximum, 8 MB or 2 GB or 4 GB or 8 GB, you keep it as RAM, so that your programs can execute faster, right? So only thing is the swap area, the swap area has to increase, and the minimum of 20 GB is required for running programs properly, okay? So you can download it and you can install it also. So that's a brief introduction about the NS2. So once you install it, then we can start with the programs what we have, and we'll show you how to create a topology, how to make a rough sketch of the topology, and how to run a code between the topologies, okay? So before we want to simulate, you have to be very clear like what type of network you want to simulate, and what are the protocols you want to run, and what are the parameters involved for a node when you run an application, because the application will tell you what are the links available, what are the node capacities it has, and all these things. So based on that we have to simulate it, and you can see the rough sketch of the topology in your NAM. You can see the topology, and then you can start running on the code to execute the programs. So the main front end is TCL over TCL language, and that has to be a little bit once or two you write a program, you get used to it. It is almost like C programming only, okay? So the back end is C++, that is you need not have to worry, it automatically compiles and you get the execution. So there are some directories in which automatically once you install it goes into those directories, and you can read the manual if you want. There is a make file, you can create a install file of the tutorials, and you can go through the tutorials also, okay? And if you ask what are the equivalent softwares available, there are a number of softwares available in the paid section. If you pay money, you get a lot of things like OpNet is there, QualNet is there. So they are like, if you try to see a QualNet package, it will be around 4 to 5 lakhs for the package itself. Like OpNet, again, it is something like 8 to 9 lakhs complete packages and all. So some of the institute might not be able to invest such a large amounts in the packages and all. But this software is a free end software, you need not have to invest, and you get almost very good simulations being done, and you can see a lot of papers have been written in NS2 and NS3, right? So now we have to create a file, and then you can modify it, and then you can compile the file also. There is an extension for the file, you have to put all the files as TCL files. Okay, .tcl is the files you have to write down. Whatever file you create, it should be in .tcl. Okay. So once you execute, you can see the results in your NAM, and you can also stop at some point or visualize more if you want. You can extend that part of the script and use it. So you can see that if you look into the NS2, you have a problem, and then in that problem you find out the topology what you want to use, and then you can execute and simulate the .tcl file what you created for the topology, and then you can visualize the results in the NAM, right? So this is the cycle what we are trying to use for executing NS2. So now we'll start creating a simulator file, and then we'll start executing it. Now so he will just try to tell you how to write a code, and then he will execute one code and tell you how to. So we are now trying to look into 4 parts. One is the hidden terminal problem. Second is exposed terminal problem. As we have discussed in the theory, the same thing we'll try to do. And then we also try to make a small network, because hidden terminal and exposed terminal, we need only 3 or 4 nodes. But we create a wireless nodes of 10 nodes or 8 nodes, and then we'll try to see how to run the algorithm and see, right? So
I'm having DSR and AODV with me.
yeah.
Hidden terminal and exposed terminal is
Come, let us start with hidden terminal and exposed terminal. Later on we go for DSR and AODV. Yeah, it goes either, right? Let's explain the code from beginning, how to create a node. Yes. Switch it on when it is ready. Keep it. Create a network and all, then we'll see how to execute it.
Let us start with the hidden terminal problem.
Yeah, the first section will be hidden terminal problem.
Basically, in NS2, set is a command we use to like create any instance or to set some values to any variable names. So here set ns new simulator will create an instance to open the simulator. So set ns new simulator command will create a new instance for the simulator, which allow us to simulate and see the simulation results. and then set trace file and set nam file. We create these files to trace and visualize the log data of simulations. So there is a two files will be created, hidden terminal wireless.tr and .nam, where nam simulation log data will be stored in that file and trace details will be stored in that file. Now we are seeing this in the wireless networks, so there will be a wireless channel and various MAC protocols. We have to set the initialize as parameters. So here set val channel, val here is the, in NS2 val is it's not a list, it's a it's like type of command where the syntax set val in closing brackets channel assigns it directly the value to the variable you have written there. Here channel CHAN PROP is like a propagation. All these are variable names, and set val will assign the values you are given to the variable names.
So when you are trying to look at that command, you can know that we are creating an area of 500 by 500, and in that we are trying to simulate a program for 10, you take 10 units of time. It can be seconds or it can be more. And you have running a AODB routine on top of it. And you can see that you have an omnidirectional antenna which can propagate through all the sides, and you have a queue, and the queue is a drop tail queue, where it says that once the queue is full, the last packet will be dropped, not the first packet, right? So, and you have priorities also in that. You can also build some priorities, and if you are not trying to take it, goes in a first in, first out, right? And the MAC layer is 802.11, which is a popular Wi-Fi network, right? And you can see that the physical layer is wireless physical layer, and the propagation mode is a two-way propagation mode. We are not taking rail degradation, multipath and all. It's a simple two-way program. Either it can go straight or if it can operate and go, that's all. Right?
First thing was we are creating a wireless channel here, and second thing, for propagation there is a two-way ground, which means it takes only the single direct path from the transmitter to receiver, and reflection will be from the ground surface. And next a physical wireless channel and the MAC protocol, which is explained by the sir. And queue drop tail priority queue means there is we'll think as a buffer where the packets will be continuously transmitted and stored in the queue. Drop tail means if when the queue is full, the remaining packets which are being transmitted will be dropped. The priority queue indicates that all the packets that are stored in the queue will be based on some priority and will be addressed and sent based on the priority assigned. And then LL means it is called as a link layer, which we use for like error control and flow control in the transmissions. And then omni antenna, which will direct the packets in all directions. And these are some coordinates and stopping time values which are assigned. And then topology we are giving as a flat grid, and val x and val phi remains like there will be a resolution of each boxes, and it forms a grid-like structure where nodes are placed in some coordinates which will be assigned in the following parts. And create God refers to the global nodes. These nodes are stored globally in the code, and we are creating the 3 nodes. Now in before code block we have initialized the parameters, and now those values are we are setting those values to the configuration of the nodes. Here set node configuration refers to all these parameters, and these values will be set to each node we have created in the code. So LL type, link layer type, which was the value assigned to the LL will be assigned to here. Similarly MAC type, IFQ type means interface queue type, which we have set as a queue priority queue. And then the antenna type, which we set as omni antenna, and all these in. And then set N0, N1, N2, NS node means we have initializing the nodes. Now as we created a topology of flat grid, we can use the coordinate system so that nodes nodes can be positioned as our wish. We have used y coordinate is 200 for every node and x coordinate is 100, 350 and then 200, so that each node will be in a straight line and we can visualize the hidden problem very clearly. Now initial node position means basically this command initial node position will be mostly used when the nodes are movable. Like this 20 refers to not the actual coordinates of the nodes, but that number 20, 5 or 10 indicates how frequently the node can change its position. Like if you increase the value from 20, it will be slow. If you decrease the value from 20 like 5 or 10, it will be fast, it will be more frequent. And then UDP. UDP refers to user datagram protocol. Like it is a protocol of sending packets. And then CBR is nothing but constant bitrate. CBR, like it is a traffic product. Like we are creating CBR means it is a traffic to send the packets.
So generally, for example, voice is a variable. So data from your email are read fast.
So UDP is like used only in wireless case. So combining CBR and UDP means CBR sets the traffic and UDP will send those packets wirelessly and it doesn't care about the errors. It's just send the packet created by the CBR traffic. And then if more and more packets are sent and there is a congestion, it even doesn't care about that. Now these are some basic parameters we have to initialize after creating CBR, like packet size, data rate, all these things. And at last there will be a delay part, like at which time the packet transmission have to start for each node. And then finally the procedure block, where procedure block includes the we have to flush all those trace files and close the NAM file and exit. It's just a formal procedure of closing all these files after the simulation completed. And then $ns run will run the code.
So you just run the code actually, then you can practice that. So those are the 3 nodes created.
So you can see the packets are transmitting and these 2 nodes are within the range of each other, but this node is not within the range of the node 0. So when the packets are transmitted in hidden node problem, like this, when these 2 transmission is going on, this is unaware of the transmission of between these 2 nodes. So if this node want to transmit to node 2, then it may think like there is no other transmissions going on and it can transmit the data. So there might be a problem of collision. That's what hidden node is doing. So even you can improve this by changing the node positions, and you can also add the feature of drop tail using this. In NS2 there is a feature of dropping packets which will show in the red color. Now even if you change the coordinates and you have increased the coordinate of 1 and move it so far, you can't see this transmission of packets from 1 and 2, because there will be 2 and 1 will be out of range. Now let us change this x coordinate from 350 to say 700. Sir? Okay, sir. Okay, let us 450. like we have to increase the resolution of the grid. So shall I move on to expose node? Like all the basic procedure, like syntax will be same for both the codes, like setting new simulator and then setting the trace and nam files and then initializing the parameters. All the values will be same. What makes the difference is, for hidden problem the minimum nodes will be 3 to understand the problem. For exposed problem we need at least 4 nodes to visualize and understand it, and then we have created 4 nodes and then we have initialized the MAC and all these parameters as before.
This is actually the time scale, you are given 10 units of time to run it, right? And that is the speed at which you are trying to run step say.
Minimum nodes for exposed node we have to require 4 nodes. So if we think as these 2 receivers are within the range of each other and these 2 nodes are within the range of each other, and if you imagine a transmission between these 2 nodes, one can send a data to 0 and 2 can send data to 3 node. So when these 2 are transmitting, if one sends a signal to 0 and it will reach 2 also, because 2 is within the range of 1. So but this transmission and the signal receiving to the node 0 is not within the range of 2 and 3. So 2 will think like the data is being transmitted and it will affect its transmission of data to 3, but actually this data is being transmitted to 0 and out of range of node 3 and it won't interfere the node 3 transmission. So this is called exposed node problem, where it think the collision may happen but actually not.
So here the same general things go on, general parameters which we are giving. So here I define wireless channel which is for simulating wireless nodes. Then we chose two-ray ground propagation model. Here we can either choose the free space model or two-ray ground model. Two-ray is more near to the reality, so we chose that.
Because in the wireless network, we don't have multi-pass now, direct one way up, like from one outlet to the other data.
So then MAC 80211, that is the standard IEEE standard. Then same drop tail queue, link layer, and we have defined Omni antenna. The length of the queue is 40 and the number of nodes are 12. And then we chose the routing protocol as AODV. So again I defined the total area as
How we do it is to make a random number of x and random number of y. Into 1x and y spaces, 1x, 1y spaces. It is not that you define exactly. You define the region. Within that you pick up one random value and keep one more. Pick up one random value and keep it.
So now we chose the area as 500 into 400, and then I will stop the simulation at 150 milliseconds. So here in NAM we generally use the time in milliseconds range. So then again we have to set a new simulator NS object, and then this is tracefile.tr where all the traces of this simulation are stored here. And then Windows versus time to, this is the trace file which we use to store the congestion window versus time. So what is congestion window is in a one acknowledgement time how many packets it can send. So that is congestion window. So that congestion window values versus time are stored in windows.tr, and the NAM files are stored in test.aodv.nam. And here we are creating the grid, so that is 500 into 400, and then we have set a channel, wireless channel for transmission. Then we are setting up GOD, that is General Operations Director. General Operation Director will supervise all the network transmissions which are happening in this code, and also it may not interfere with the routing protocol, but it checks whether all the nodes are within the range of transmission, and it checks whether the nodes are movable or not, and their mobility also. So GOD operates with that. And then we have initiated all of them, and for each node we are initiating all the routing protocols, link layer, MAC type, IFQ type, IFQ length, antenna type and propagation type, etc. So now this loop is for setting the initial positions of the nodes. So for each node we are as there is no z axis, we are keeping it as 0. For x and y we are just using 10 plus int of rand into 480. So rand function will generate either 0 or 1 values in between 0 and 1, then it is multiplied by 480, and what does integer do is the integer value of that rand into 480 is taken and plus 10 is added for it. So this is the x position for different nodes, and this is the y position for different nodes. And then what we do is,
So this is very important. The location of x and y, you can randomly select. You do not have to fix like read or something, right? If you want to create 100, it is easy for you to create. Okay, only thing is you have to expand the area and just.
now this is for mobility. As in AODV, the nodes should move. So what we do is we already define initial nodes, and then this is for setting the destination from where it should move to the destination we are setting here, that is expression of 10 plus int of random into 480. this expression command will calculate the value of the highlighted thing and then give it to the set destination value. And next, this is for mobility, like setting the speed of the nodes. So this here we are using random mobility motor. So this will control like how the nodes should move in the grid. And same again, so 2 plus int of random into 15. So here the speeds will generally in between 2 to 17. Then as we need acknowledgement in this AODV, so we are setting up TCP protocol, and then I am initializing communication between node 2 and node 8, and here node 2 is source and node 8 is sink. And I am also initiating the FTP application over the TCP protocol. So FTP will generally set the traffic, and then TCP is the protocol which it follows. Here I am also initiating.
TCP we have actually file transfer file we are trying to run. It's almost like parallel TCP.
And also I am setting up communication between 0 and 5. So we can have like 2 different cases which while we are observing the simulation. And here this is the procedure for printing the plot window size, that is the congestion window versus time, like how the congestion window is varying with the time, how it is increasing and how it is decreasing. This is the command for this is the variable, and this is the command for initializing that congestion window. So initially congestion window will start from 2 and then it doubles over the time. If there is any collision, it decreases again and then it increases if it needed.
2, 4, 8 and then it drops back.
And this is for telling each node when to stop the simulation. And this is the procedure to run the whole code, and $ns run is for running the simulation. So we have set up communication between 2 and 8 and 0 and 5. So now the nodes will start moving after some time as we given random values of start time.
So you can see the data packet and the acknowledgement packet, small packet.
So now see, like 5 is moving, and so as 9 is in between 2 and 8, it is using 9 to create the route in between 2 and 8. Initially there was like no number 9, but now it is using 9 to transmit between 2 and 8. Now if other nodes come in between the 2 and 8, then it will use other nodes to calculate the optimal path in between 2 and 8. So then it will transmit. So same in the case of 0 and 5 also. You can see now like how the random mobility motor is moving the nodes.
So now 2 and 8 is done. So if the distance increases, then it has to take another.
So now 9 went in between 0 and 5, then so it used 9, and now 9 crossed. So So now 1 is in between this one. In between, if there is any collision, it also drops the packets, but as it is random, sometimes it happens, sometimes it doesn't happen. Yeah, yes.
Randomly to something, events, there is some movement, only there only it moves. So you can define whatever pattern you want, it moves to that direction. You want all to move up, it can move up. All to move down, it can move up. Or randomly you can move only some area you can move. But you have not compiled it.
I have compiled it again.
Basement of the nodes are there. It's not that it will come to the same place. The 5 and 0 are communicating, 2 and 8 are communicating. So now, today morning sir was discussing of keeping minimum distance between nodes. That also is very important. Zero and 5 are isolated now because the 5 and 9 has no connectivity, 0 has no connectivity.
Here the communication in between them also depends on like power of transmission which we are using. Initially we have defined that. If you see like 0 and 5 are communicating using 3 and 9 in between. Next.
We keep it like that.
DSR.
Have Gian will come back. And we start giving you the code. You can use that.
So in that parameters, that antenna and whatever parameters, they are fixed or we can change.
We can change. We can.
Can you go back to the code?
Yes.
There is a, we have placed these nodes in a random fashion. You can define a grid and you can place them in the earlier case we placed them on numbers. We want 3 of them on the same line. So we took Y as 200, then 100, 300, 400 we have done.
How can you optimize your antenna or whatever?
So antenna is only communication range that we define. That has only this much distance that we define. So if it is unable to reach, we hop it through some other node.
So you can't change that parameter.
So you can change the antenna parameters. You can say that you can say that okay, it can go only to 2 units or 3 units.
Here we can define extra attributes if we want for an antenna.
So the XL by 500, 400, right? So you can define the nodes. Just go to the node. Here the node, if you see, here it is a random statement and type it initial position. Instead of that, you can give 50-50. It goes to 50-50. Right? Instead of that, here it wrote X, Y, Z value. Z is 0, one plane is 0. X value is a random value between 10 and 480. Right? And here also 10 to 390, 490 and 390. 10 plus 480. If random value is 1, if it is 0.1 or 0.2 or 0.3, equivalent points will come.
These can be simulated in a 3D also.
Yeah, you can have Z also, you can activate. But here we are taking 2 kinds because we assume that one height only. Because all you are bringing to one height. So in height you can do. Or if you have different heights, you can change Z also. That's the main aim of it. So we'll have Gian come back. We'll give you the code to just run it on your laptop and see. We run DSR algorithm, and once the DSR algorithm is complete, we try to get back to the running on the codes on your laptops and all, right? So basically in the DSR algorithm, it is almost similar to AODB, and we'll see how the program runs. So if you try to see the code, all the files are same. You are setting the values to some parameters like channel, propagation, MAC, and all these things. You are setting the values, and then you are setting the network simulator pad, scratch pad we call it in other language. You can see the NS simulator is being initiated, and then we are creating 3 files. One is for trace, one is for Windows versus RAM, and one is for NAM traces. And then we are trying to set up the topology. And here the topology, we are creating some LAN nodes, something like 12.
Yes, sir. Same
12 nodes, same type of node. And we are also giving the nodes placement as random. And they are also placed between 10 to 480 and 10 to 350, 380. And they are randomly placed 12. And we run a DSR algorithm instead of AODB. Right? Continue.
So the major difference in before code AODV and DSR is here we are setting up the routing protocol as DSR, and then everything is same, and here we are defining the antenna power. Actually by default it takes us 0.28 watts, but if we want to change the antenna power so that for how much distance it can transmit,
Power tell you how far you can go.
so that we set here, and then everything is same again, initial positions and setting Z value as 0, and then here we are setting up the speeds between 2 and 17, and these are the these are the destination positions for each node.
If you want to make it faster, you can increase it to 20 or 25 so that they move faster, right?
And then we are setting up the same TCP routing protocol and also FTP application over each route. And then we are initiating communication between 2 and 8 and 0 and 5. So, and everything is same as before AODV. We'll run the code once. So, if you see the highest distance it can transmit is up to 424.5 meters.
Window is only 480.
Yeah, yes. Sir.
So you
500 into 400, right, sir? So in one direction it is more.
the other direction,
It's less.
so you might not be able to see the wrong packets.
So in simulation, like there is no particular difference in between DSR and AODV, as they both find the same optimal route, or they optimize on the base of number of hops it takes. But when we want to print like repeat requests or repeat errors which it transmits in between the nodes, so there the difference will occur in between DSR and AODV.
Can you change 2 and 8 and 0 and 5 to some other values?
Yeah, yes, sir.
And you make 3 or 4 also active, only not only 2.
Okay.
You copy that into another one,
Yes, sir.
so that you can understand much better. The same set you have to copy if you want communication between other nodes also. So the node numbers you say, right? These are the things that change. You say so 1 and 7 is over, 4 and 7 is over. So you put 3 and 6 and 2 and 8. So those are the packets they are planning to exchange, and we see how what will happen. Then we have to copy the user also, not only. The text also you have to change.
Yes, sir. Yeah. Okay. I think it's fine. Then I'll keep different numbers here. Then here also I should see. Yes, sir. One, two, four, five, set. Yes, sir. Then two. Attach agent is command only, sir. I think. Yes, sir. Here I should change. There is some error in that. Once I'll change the starting time. Everything is fine, sir. I don't know why they are not moving. Should I change this classes also? Course. Initially it was like 2 and 1 and 1 and 2 only. Yes, sir. movement is happening like very late. Which one, sir? Like stop time? Yes. Stop time is decreased. Yes.
So just try to run the code for export and detail as well. Once you complete, then we'll get back to you.
Yes.